MET 335 Exam 2 Study Guide. First off, for all topics, you should be comfortable describing the equations we worked with, and you should be able to say how they are properly calculated using a given equation. Would change based on changing one of the variables or terms in the equation. Firstly, we'll deal with Rossby waves and the calculation of beta. So remember that beta is just equal to df dy, and it's also on the equation sheet. And it describes how the Coriolis parameter changes with distance instead of with degrees on the Earth's surface. So, Rossby waves propagate due to vorticity advection. For example, at the base of a trough, vorticity is advected to the east, which moves the base of the trough to the east, vice versa at the ridge. So, remember that perturbation from a stable balance leads to Rossby waves, and perturbation from an unstable balance leads to disturbances. Example would be baroclinic instability or cyclogenesis. So, Rossby waves exist due to the conservation of absolute vorticity. Remember that when absolute vorticity is conserved, any increase in planetary vorticity must be accompanied by a decrease in relative vorticity. And planetary vorticity increases as you move away from the equator, meaning that relative vorticity must decrease. So, nearer to the equator, you'll get a trough because relative vorticity is more positive. And as you go north, you'll get a ridge because relative vorticity is less positive or eventually negative. The tendency here is toward geostrophic balance, and the Coriolis force is a dominant restoring force from a perturbation. Remember that according to the equation, C equals mean of U minus beta over K squared, and K equaling wave number. So since that K is on the bottom of the equation, and the equation is being subtracted from U, that would indicate that a larger wave number would increase propagation speed, because C would then equal U minus a smaller number than would otherwise be if K was smaller. If a wave is stationary, then C, or phase speed, equals 0. And short waves move faster because they have a weaker propagation to the west, and long waves move slower because they have a larger propagation to the west, which slows them down. Because a longer wavelength has a smaller K in the denominator, making the propagation to the west larger. So, here are some basic properties of waves, and these are all definitions from class. So firstly, wavelength is the distance between periodic spatial repetitions. For example, from trough to trough or ridge to ridge. Frequency is the rate of recurrence of any period phenomenon. Amplitude is the greatest magnitude at a given point of any spatial and temporally varying physical quantity governed by a wave equation. Group velocity is the velocity of the envelope of a group of waves of nearly identical frequencies. Dispersion relation is a functional relation between wave number and frequency for a plane harmonic wave. Phase speed is the speed of propagation of a surface of constant phase in a time harmonic wave, and wave number k is the number of waves in the distance 2 pi. Next, we'll deal with gravity waves on the small scale. Gravity waves are stable and small scale because they involve a small scale perturbation on a stable surface. If the surface was unstable, you just get convection. So for a stable atmosphere, stability restores balance, which means the perturbation-initiated oscillation would result in waves. For an unstable atmosphere, perturbation results in growing disturbance. Motion does not equal acceleration. So remember that the process goes like this for perturbations in a hydrostatic balance atmosphere. The parcel is placed up by some force, and then the parcel is accelerating downward, and it moves down as it's accelerating up once it passes that stability point. And then the wave moves up and starts accelerating downward again. In an absolutely unstable atmosphere, the parcel will continue to accelerate vertically in a direction up or down of its displacement. If you'd like more practice on interpreting diagrams of gravity wave thermodynamics and kinematics, just look at homework 5. There's also some videos linked on the study guide. Next, we'll be talking about Kelvin-Helmholtz waves. So, the conditions required for Kelvin-Helmholtz wave development. Remember that the Ri number is equal to buoyant stability divided by vertical shear. And if there's wind shear, then the bottom is positive. Buoyant stability in the Bulk-Richardson number equation will be positive. If the Bulk-Richardson number is stable, positive, and less than 0.25, then it will be favorable for KH waves. Another way of saying this is just between 0 and 0.25. If it's 0 and there's no vertical wind shear, this means that it's neutral and thus not favorable for KH waves. And if it's negative, that means it's buoyant, unstable, and not favorable for KH waves. Next, we'll be talking about baroclinic generation of vorticity and baroclinic instability. So, some differences between a barotropic and a baroclinic environment. In fact, they're exact opposites. In a purely barotropic flow, pressure and density gradients are parallel. Remember that barotropy is a state of zero baroclinicity. Under barotropic conditions, absolute vorticity is conserved. The geostropic wind has no shear with height, and thus there's no thermal wind. Baroclinic, on the other hand, occurs when pressure surfaces intersect with density surfaces. This is where all the fun weather comes from, as well as having a horizontal temperature gradient. To make it simple, barotropic means no horizontal temperature gradient and boring weather, and baroclinic means there is a horizontal temperature gradient and there's fun weather. So, to quantify the development of vorticity in a baroclinic zone, you can just use the baroclinic generation term from the vorticity equation on the sheet. And this is the term in the equation on the sheet that deals with changes in density and pressure. So, when it comes to interpreting a graph with thermal wind and wavelength axes, remember that where delta equals 0, this separates stable and unstable waves. The area where it's unstable and with the thermal wind encourages the disturbance. Remember the equation associated with the graph, and that when you get an imaginary number as part of the answer for this equation, you'll get unstable waves, or baroclinic instability, is another way of saying that. AKA anywhere outside of the bowl of instability on the graph, in quote unquote. Remember that if wavelength is too small, it will be stable no matter how high the thermal wind is. If thermal wind is too small, it will be stable no matter how high wavelength is. So, covering mountain waves next. It's important to know what a hydraulic jump is and how it relates to the location of strong winds in a mountain windstorm. So, the hydraulic jump is where we have the strongest winds, and it's where we transition from a shallow and laminar flow to a deep and turbulent flow. For example, you can see this where water strikes a sink. So next we'll be talking about Froude's number a little bit. Remember that Froude's number is denoted by the term FR in the equation, and mountain waves are favored when this number is equal to 1. So, on the upstream side of a mountain, flow is accelerated due to pressure gradient force associated with the mountain wave. The mountain wave breaking on the downward side of the mountain causes a hydraulic jump-like phenomenon, and the flow transitions from wave dominant to supercritical. Remember that U in the equation is upstream wind speed, N is the typical Brunt-Väisälä frequency, and H is height in this equation. So, one last note about Froude's number is von Karman vortices. And it's a cloud vortex generated on the lee side of an island barrier under conditions of a low-level temperature inversion. The flow frequently forms a trail of counter-rotating vortices, alternately placed in two parallel rows.